every industrial plant begins not with the steel, the concrete, the pipes, the buildings, the facilities associated with them, but with a process model that transforms ideas into realities. And that is where process simulation comes in as a tool for creating such a process model. My name is Peter Oladipo, and in this masterclass, I'll be showing you how process simulation is applied to the design of an industrial plant, and in particular to the design of a plant for the conversion of flare gas into high-value petrochemicals. Now, gas flaring is a process of burning natural gas that is produced alongside crude oil as waste because of the lack of adequate infrastructure to convert or properly utilize this natural gas. So they are burnt away as waste material. Interestingly, natural gas worth over $54 billion are burnt this way annually all over the world. Besides this monumental economic losses, there's huge environmental degradation associated with this gas flare. So in this masterclass, we will be developing a process to convert this natural gas that would have otherwise been flared into olefins, which are basic petrochemicals that are used in production of virtually everything around us, from plastics to rubber to textiles to automotive materials to medical devices, you name it. And the platform we'll be using for this simulation exercise is called LensaSim. LensaSim is a web-based process simulation platform that we develop at Lensa Technology to simplify process simulation and to make it easily and readily accessible to everybody. You don't need to install any software or pay for expensive licenses to access it. All you have to do is to visit lensasim.com and you're good to go. Okay, but before we start with the simulation proper on lensasim.com, we need to understand the nature of the feed we'll be dealing with. This is a representative sample of the conversion of the feed of the flare gas from a Nigerian feed. As you can see, it's majorly comprised of methane, C1 hydrocarbon, and about 20% C2 plus hydrocarbon from methane to C6 plus. And then the acid gases and some other items, right? And this is on a dry basis. Okay, we'll go into more details as we go along. Now, the process for converting this flare gas to olefins can be represented by this blood flow diagram, right? And you can see basically involve conditioning the gas, essentially treating it, preparing it to be suitable for downstream separation and reaction steps. So conditioning then to the proper reaction steps in steam cracking and then olefin recovery for separating the product. They will go along that way. Now, this is a very simplified block flow diagram, like I said. In reality, in a real plant, you have hundreds of units, hundreds of equipment that define this process we are saying here. Okay. So even for this simulation, it is impossible for us to, or let me not say impossible, it is difficult. It will be difficult for us to simulate the entire plant in one sitting. So we'll be dividing this exercise into 5 parts. Okay. So part 1 would be about the gas condition itself, that is preparing the gas to some simple processing to make it suitable for downstream processing. And then there will be cryogenic separation in part 2. We define what that means later on. There will be steam cracking. In part 3, there will be olefin recovery, and then there will be plant integration, utility, and optimization in the final part. So, but of course, for today, our focus is on the conditioning of the gas. That is what I define as essentially preparing the gas to be suitable, because if gas needs to be in certain condition to be suitable to be processed in downstream equipment. Okay, so we now move to the simulation platform now to continue with this exercise. So I'm going to stop sharing and go to LensaSim.com. Okay. Okay, so this is lensasim.com, and as you can see, is a simple platform. It's straightforward, and all you have to do is to click on Open Simulator. You could also click start by just clicking on Start Simulating Free. You're good to go. It's good to start by just clicking on Open Simulator. They did it the same place. Okay, so we click on Open Simulator, and so we are here, and one thing I would show us is there's this guide system. So there's LensaSim as a guide system for first-time users. So you can turn it on, and it usually guide you through the process, right? But for this exercise, we'll be turning it off. So the guide is off, right? So to start any simulation exercise, the first place we need to come to is the properties environment. As you can see here, there are 4 environments here. There is property environment, simulation environment, analysis, and economics. Okay, we go through them one after the other as we proceed with the progress with the simulation exercise. Okay, but the starting point in all cases is the properties environment. This is where we define the feed composition and every other species or component that will be involved in the process, including the products, any intermediate products, and any chemical, right, or any material that will be involved in one way or the other in the processes, right? So for now, we'll start by defining the feed, okay, because that is what is defined to us right now. So we define the feed. Of course, it contains methane, contains ethane, it contains propane, isobutane, and N-butane, N-pentane, then hexane. This is before that. Let's do it in the order in which the feed was provided. So I'm gonna look it up quickly. Okay, so N-pentane, then isopentane, isopentane. So one thing you could see is any component that you can't readily find or see, you can always use the search button to find them. So isopentane is there. Then heptane. So hexane, we go to hexane now. Okay. So, 10. Then there is on it. And there are acid gases, there is nitrogen as well contained. So, okay, so we've defined, essentially specified the components that makes up the feed that we are given. That is the flare gas now. So the next thing we need to do is to determine or define the property package, right? Like property method or property package is a thermodynamic property that essentially defines or that would define the behavior of this component during the processes, either the separation processes or the reaction processes. So the thermodynamic package that defines the behavior that essentially will predict, like a predictive system that predicts how these components will behave or we perform under different conditions, right, of the process we want to develop, is what we known as property method, right? So we have to specify which property package best define these components and the processes will be surrounded them to. Now, pentgopsin is a typical package that is well known in the petrochemical industry, right? It's typical for this kind of process, and it's suggested here by LensaSim. So we're going to go with pentgopsin, choosing pentgopsin. So once we've done that, the next step is to just continue to simulation. Okay. So we are now in the simulation environment. Of course, what we've done in the properties environment is to specify the component and then define the property package to go along with, and that you see at the right column here of the environment. Now, We will now need to, of course, the process will now begin to be the process one after the other, starting with the feed, specifying the feed itself, right? So what we've done is to specify the component, but we need to define the feed. That is, specify the composition of the feed, define its temperature, its pressure, and other important parameters. So for C here in the specification form, we need to define the temperature, we need to define the pressure, we need to find the flow rate, okay, the flow rate, and then the mole fractions of this component. Okay. Now, to find the data for this, you can always do research. Research you want to do is to find out the typical properties, right, of flare gas, for example. What is the typical properties of flare gas when it come out from the oil well, or what is a typical property of the gas as it is entering its kind of process you want to build to process that gas. You understand? So you do those research to find those data. So I've done some preliminary research to find those data, and I'm going to be using them here. Okay. So the temperature is 35, the temperature, and the pressure is in bar is 31 bar. So this is so as the gas is coming out and entering the very first unit, okay, it's coming in at the temperature of 35 degrees Celsius and at the pressure of 31 bar, right? Then the flow rate will be using the standard gas volume basis, and the basis in million standard cubic feet per day. So we're using 20 million standard cubic feet per day. So what we are saying here, we are assuming that the volume of the gas that is coming in, right, is 20 million standard cubic feet per day. And of course, the mole fraction, just as what I was saying in the slide I showed for the composition. So that's maintained of 78.8%, ethane 10.50, propane 4.62, iobutane of 0.79, and butane of 0.97. Then N-pentane, we have N-pentane of 0.31. So N-pentane of N-pentane of 0.27, I-pentane of 0.31. Hexane, so we don't have defined compositions for the C6 hydrocarbons, that is hexane, heptane, and octane on an end. So what we are going to do is we're going to lump them together, as assume that composition is hexane because it's just 0.42%. So it's not a bad assumption. So we're going to assume lump them together. So it means that the feed for heptane, octane, and then will be empty. Oxygen is 0.61%. Carbon dioxide is 2.6%. Then hydrogen sulfide of 0.02%. Right now, as we put it, see this specification and in percentages for this is more fraction basis, so it needs to be it needs to sum up to 1. So we're going to normalize. By clicking normalize, LensaSim is to calculate the composition as a mole fraction. Okay, so with this we have fully specified the feed as it is entering the process. All right, so let's just name it as flare gas. We name it as flare gas. Now I should note that this flare gas is coming in on a dry basis, right? On a dry basis, that is, we don't have water vapor contained within this gas in this composition, which is not the case ideally. In reality, you have water vapor contained in that gas, and as well as hydrocarbon condensate. You know, this gas is coming out of an oil well, so some of the hydrocarbons, the crude oil, are condensed in the flare gas, right? So you have water vapor in the gas, water contained in the flare gas, as well as hydrocarbon condensate. So that means that we need to resolve that by specifying a two feed stream, right? So we specify two feed streams for and it's based on what we have, right? This is based on what the data we have. Okay, we could have specified everything here, so there is no formula for doing that, right? We could have specified everything here if we have a feed profile that includes from the onset both the water and the hydrocarbon condensate. We don't have that. We have three separate feed profile from the data that I gathered, right? So one for the flare gas on the dry basis, and then the other two streams are one for condensate and carbon condensate, and another for water. So what we're going to do is to specify those additional streams and then mix them together to now form the realistic flare gas as it will be entering the process. Okay, all right. So we'll be specifying two more feed streams. And we can name this as dry flare gas. Okay, dry flare gas, and this will be named as let's call this water, free water. Yeah, and then another feed stream. So we're going to call HC condensate. Okay. Now, you would notice that in our properties, in the properties package, water was not among the species that was defined. So that means we need to go back. Yeah, I told you we can always go back and forth between the properties environment and the other environment as need be. So we can go back, we'll go back to properties environment and specify water because it was not originally specified. So let's find water and just search for it. So it's water. Okay, so it's included, and we can go back to the simulation environment. Okay, so that what is what I've specified. Of course, it will be expected they are also coming at the same condition, same temperature and pressure. Of course, different flow rates. Okay, so I have the data for that. So I'm going to specify the free water specification that we have. Of course, a temperature of 35, pressure of 31 bar. Right, pressure of 31 bar. Okay. Now we have it in mass flow rate, mass flow basis. Okay, mass flow basis for the free water now. Okay, let me see what it is. On this 500 kilogram per hour. So that you can always change the unit basis here. Then we have the mole fraction for the water. Majorly water, but it also has some other species within it, right? Few other species. Okay. So 9.8%. 9.8% water, and 0.05 for methane. That's some 0.05% methane. Then 0.10% CO2. 0.05% H2S, hydrogen sulfide. So we normalize, okay, these in percentages, so we normalize for mole fraction basis. So this is what we have, right? So it's, of course, it's free water, but of course, based on industry standard, typically it also has the some of the hydrocarbon dissolved in it. So that's what we are specifying here. Okay. Then the hydrocarbon condensate essentially will be the heavier hydrocarbons. The heavier hydrocarbons. Okay. So that also we need to specify. So what do we have for the specification? Also, of course, at 35 degrees Celsius, coming in at 31 bar, as with the others, on a mass flow basis, as heavy liquid on a mass flow basis, and it's coming at a feed flow rate of 150 kilograms. So entering the carbon condensate 150 kilogram per hour. And the feed composition, we have methane 0.5%. We have ethane of 2.0%, propane of 7.0, and there's iButane of 8.0%, and butane 12.0, isopentane 10.0%, N-pentane of 14.0%, Azane 16%, then of 14%, and we have obtained C8 8%, and C9 on name. Now we don't have defined compositions, just like the same thing we had with the dry fleckers. Don't have defined composition beyond C9, beyond the name. So we're going to lump every other species beyond the name, that's C9 plus, into the non-name feed of 8.5%. So we're going to assume everything is just non-name. Okay. All right, so normalize to be in most fraction, and this is what we have. Okay, so we have representative samples for the three primary components that ordinarily would be in the flare gas as it is exiting the oil well. Okay. Now, so we have this, just use a mixer. We have a mixer here to mix them together so that to be as though the way it should be. All right. Now the mixer, as you see, that's 2 inlets, but you can always adjust it here. Click on it, the mixer. That's because we have 3 inlets, right? Flare gas. So you have to do is to place your cursor here and just drag it. It's very easy to do. I'm going to retract this. Okay. Right. Second stream. Yeah. This goes to the third one. All right. So we have those 3 streams entering into mixer, and then the product stream, that is what is coming out. So this is the actual flare gas. Okay, so let's call it actual flare gas. Now, there's a naming convention that is applicable in process design generally, especially with the streams. Okay, with the streams especially the product stream. I mean, yes, typically in most cases they are same as a stream. It's in the naming. But the streams are like the pipes, the pipelines that convey a species from one point to the other. Right? So there are certain conventions for doing that. So to make it easier for it, we're going to use that similar convention. So for the gas stream, okay, we're going to name it as starting with G, letter G, and then 3 numbers, right? 100, right? For the water stream, we're going to name it starting with W, 10, same. The other one will be, next one will be 101, and so forth. Right? For this to be, we'll name it H at carbon 1. Okay. Okay, so this is the gas, still the gas actually. It contains the impurities now. 101. It contains other constituents now. So it's still treated as the gas stream. So call it G101. Okay. So they are mixed together. I mean, there's nothing to divide in the mixer, right? So we can either run it now, just solve for the simulator to solve this, just this simple unit, the mixing of it, or we can wait till we finish with the building of the flow sheet. It's a good idea. I recommend sequentially solving the flow sheet by just running it every time you add new unit and complete specifying a process. In this case, it is a complete specification. You can run it, okay, and see what we have. All right, so we've run it and the solver has solved the flow sheet, right? So you could see what has been done here, just simple mix. Nothing is happening, right? Just mix, right? To have the way the flare gas should actually be before entering the process. So if you look at that, that is G101, right? Stream G101. See what we have here. It's what is being mixed. Look at the composition. Let's choose this as a mass basis mass flow rate. So we see what we have. You see that essentially all that G101 of in G101, H101, W101 are now contained in G100, H101 should be 101, W100 are contained in now G101. See, right? See that, right? Nitrogen, just summation of everything, just containing 101. That's what we have. You can make it, simplify it by double clicking here. Let me first change this. There's an error here. H1. So we can double click this, right? Double click the midstream and just call G101 and see what we have. See, as all those species, right? This must have in the move function. The methane, right? 74%, right? The move function has gone down a bit because of other things that have been added, like water, right? You have water, methane, and the heavy hydrocarbons. See, so everything's contained. Okay. All right. So we've done that. Now the next thing is to now start with the first process, the first proper process for this separation, for this gas conditioning. And that would be, I mean, essentially what we want to do now is to do the reverse of what we've just done. Okay, so in the industry, you use what's called a slug catcher, right, to separate the liquid stream from the gas stream. Because what we have here in this gas stream is not just gas. It has this condensate and this free water are actually liquid for the most part, coming as liquid together with the gas. So as the gas is sitting with some liquid content. So what, and solid, in fact, some entrenched solids, right? So what we are doing in the next step, what we do in the next step, will be to actually separating the phases. Okay, separating the phases, the three phases, the gas phase, and then separating out the liquid and the solid phase. Of course, the two liquid phases actually, there's a water phase and a hydrocarbon liquid phase, and then there's a vapor phase. Right? The solid get entrained in the liquid phases. Okay, so it's important for us to do that. We need to first separate the gas out completely, not dry gas. It's different from dry gas, but separate the gas out with some condensed hydrocarbons, some condensed water and other species, but it needs to be fully gas. It needs to be completely vapor phase. That is what we'll be doing next. Okay, so we'll be using, in LensaSim, we have a unit called three-phase separator that does that job. Excellent. Right, so three-phase separator. So what we do is just send this G11 to this three-phase separator. Okay, and then because it's going to be one another product stream. So this will evidently be the generally be the gas stream, the new gas stream, right? Call it G102. Okay. Then this will likely be the water stream. We call it we have second, so by W101, W100, so it's called it W101 for water. For the hydrocarbon, we will call this H101. Okay, so this is still the flare gas, right? So flare gas, we can just call it, let's call it flare gas as it is. Just call it flare gas. Without, so it's completely gas, right? Vapor fraction is 1. That's what we're going to achieve here. Okay. Here, so you can just call it free water. That's the final product. And HC condensate again. Okay. So we now have to specify the slug catcher, the three-phase separator. Okay, specify the temperature and the pressure for it. So I mean, these are defined also in the literature. We do some research, you find out the typical conditions for a slug catcher in the industry. So I have those data as well, and I'm just going to look them up to be specified. Okay, so I'm going to look them up quickly. Okay. So the temperature is essentially the same as the temperature of the feed and the pressure of the feed, from what we're saying here. So feed temperature of 35 degrees, temperature of 35 degrees Celsius, and a pressure of 31 bar. So it's usually the same as the feed conditions. Okay. So with that, we've fully specified the condition for the slug catcher. Okay, and let's see what's going to happen. So let's run it. Okay, that's been solved. Okay, let's see what we have. Okay. So we're going to look for G102, W101, and H101. Let's look at G102. So G102, you have methane coming compared to G101 now, right? And then the others. Okay. So we have, of course, all the methane in the gas stream. From G101 goes to the gas stream, right? Then let's see what goes into H101. H101 has some, because that's very minute amount of the methane, right? Virtually all of them has gone to G102, right? Some very minor portion of it has gone to H101 and W101 as well. So we see, okay, there's W101. Some has gone to W101 as well for methane and ethane. That's for the hydrocarbon of interest, right? In the flare gas. Okay, but of course, if you look at the water, right, a lot of this has gone. But let's use. Okay, okay. Something was blocking there. Okay, so look at the water. You see that in G101 we have 498 kilogram per hour, right? Specified. Now you have 15.9 in G102, and in the water, the W101, see, almost everything is in W101 now, right? We still have some in, of course, some of the water contained. There's some water contained in the hydrocarbon itself, carbon feed, both the condensate has some water as well as the water itself. Water stream also has some water. So you can see most of the water has gone to the water stream, right? Okay. Sorry, we have H. There's a confusion here. That is all going to H101. So this should be H101. This should be the water stream. Okay, this should be water. Okay, this should be W101, and this should be yeah, the common condensate. Okay, let's see. There's an error here. So this should be HC condensate. Let's just check. That's very what. Okay, let's run it again. Okay. Yeah, I think there's an error indeed. There was an error. So let's see what we have. So you have the water stream now. Yeah, in W101, as you can see, right? So the water has gone to W101, right? Water stream, exactly as intended. So G102 has some water still, of course, but you can see that most of it has gone to W101, the water stream, right? And for H101, the hydrocarbon condensate, you have most of the heavy hydrocarbons. See here, ethane, ethane, nonane, right? Most of them have gone to the H101. Call it H102. H101. Oh, we have H101 before, so this should be H102. This should be H102. Okay, so H102, yeah. So H102, as you see, a lot of, just from more like a representative of what we have in H101. So we found them in H102. All right. So with this, we've done essentially separated the phases, right? The solid and liquid phases away from the gas phase. So the flare gas now is entirely a gas stream, right? There's no liquid, and we'll confirm that by looking at, let's look at the phase G102. See, vapor fraction is 1, right? The vapor fraction entirely vapor, right? No liquid whatsoever. Okay, so it's entirely a gas phase, though we don't have any liquid or solid phase in this flare gas stream. However, we are not yet done, because we still have condensed water vapor within the gas. I mean, it's existing as a gas, not as a liquid, it's existing as a gas in the gas phase. Also, we have acid gases, H2S and CO2. Let's open that up, or let's check from here. You see what I'm talking about? G102, right? This is G102, right? So we have CO2, you could see significant amount of carbon dioxide and hydrogen sulfide contained in that stream, as well as water. Now, we must remove these three before we can proceed with the process, before the process can go to especially cryogenic separation. And I'll explain why. Now, cryogenic separation involves is a low temperature process, right? Sub-zero temperature process. The operating temperature is usually below 150 degrees Celsius. Okay. So at that temperature, of course, water will freeze, right? It's going to freeze. And it's going to top. So that solid will be a challenge for equipment. I mean, it's going to damage equipment, damage the pipes and what have you. So you don't want to have ice being formed within the downstream process equipment. I mean, you don't want to damage millions of dollars of equipment. Right? So it is important to remove that water vapor before we proceed with the next steps in the processing. Similarly, we have to remove carbon dioxide. Carbon dioxide, just like water, also freezes out at very low temperature. Okay, so in the same way, just as we have to remove water vapor, we must remove carbon dioxide. Besides it also being an acid gas that could lead to corrosion, okay, that will also damage equipment. And also hydrogen sulfide will lead to formation, will lead to corrosion. Sulfide species will be formed, leading to sulfide corrosion and what have you. So these will damage the equipment. I mean, cause the plant to shut down and be ineffective. You could set up $1 billion plant, and because of the presence of these species, however minute it may seem that they are contained in G102, they can damage the $1 billion equipment and render it ineffective. So they must be removed before you proceed. All right. So this is what we'll be doing next. Okay. So the first thing we'll be removing the acid gases, CO2 and H2S. There's a specialized unit for doing this in the petrochemical industry. Right? It's called the amine sweetening unit. Okay. So it's called the amine sweetening unit. And what it does is it's an absorption tower, and you essentially send the liquid and absorb that contains an absorbent, right? It comes from the top of the column, and then the gas will feed the gas from the bottom of the column, and then they contact each other, of course, and then the absorbent removes CO2 and H2S, in stages from the flare gas. Okay. Now the species, the absorbent typically used for this process is called MDE, methyl diethanolamine, right? So that is the compound used for this amine sweetening unit. Okay, in LensaSim we have an amine contactor, specialized unit that's created in LensaSim for this purpose. So we're going to just bring out the amine contactor. Like I said, is essentially an absorption tower, right? So the flare gas, of course, we go into the bottom, right? The gas, see where in the inlet we have a G, means where the gas enters from. Then the liquid is where the MDA will come in from. Okay. So remember, we've not specified MDA as well in the property package because we've not gotten here. So we are going to go back to property and specify it, right? So let's search for it. Let's search for MDA. Here we have it here. Methyl diethanolamine. So we pick it and go back to property package. Right. All right. And then of course we add a feed stream for this. Okay. So that's the feed. Call this MDEA. So let's call it M101, right? M101 or M100. Okay. And for the product stream. So as the flare gas is coming from the bottom of the column, rising to the top, of course, it's going to be coming out at the top. So this is going to be the gas. This is where the gas is coming out from. Okay. So this will be G103, right? Following the naming convention for the gas stream, right? G103. Okay. And this will be M101. Yeah, just call it sweet dry gas. Right, sweet gas. Call it sweet gas. Okay, because it's not sweetened, because well, at the end of this step, we would have removed CO2 and H2S. Okay, we're going to call it sweet gas, right? And because this is MDA, just MDA. Right. Okay, so we need to specify the two things. We need to specify the MDA component. The composition of the MDA is conditions, field condition, and whatever. And of course, we need to specify the unit itself. Okay, so let's start by specifying the MDA. Now, also, you do research to find out what are the typical conditions and fit profile for this compound, right? That has been done. So let me look at what we have for MDA. We have so it comes in as not as pure MDA, it comes in with water. Okay, so it's coming as 45% per weight percent MDA, the remaining 5% being water. And it's going to come in at the temperature of 35 degrees Celsius as well. It's just the same temperature as the feed, and at the pressure of 33 bar. Okay, it's going to come in at 35 degrees Celsius or 40 degrees Celsius. Mean amine temperature, yeah, 40 degrees Celsius. Okay. And a pressure of 33 bar. Okay, so let me specify. Choose BF bar first. So 33 bar, and at the flow rate of 15 meter cube per hour. Volume, just actual volume flow rate. So the flow basis will be in actual volume, right? At temperature 50 meter cube per hour. Okay. Now, and is mass fraction now, right? Mass fraction with the MDA being 45%. I just say 0.45 fraction. That is it, and 0.55 for the water, right? So that's normalized right away because that sums up to 1, right? So that we specify the feed condition for the MDE that's coming in. Okay. Now we're going to specify the conditions for the mean sweetening unit itself. As the pressure of that river as well, and the temperature of the number of equilibrium stages. Yeah, number of equilibrium stages, very important parameter. 20 stages is assumed as is recommended from preliminary findings. It's so 33 bar being the operating pressure, and two important parameters we also need to specify are what are known as carbon dioxide approach to equilibrium and the hydrogen sulfide approach to equilibrium. So the C2 approach to equilibrium essentially tells you as the gas leaves the equilibrium stages, because the equilibrium stages, how much of it approaches equilibrium, right, as living with the solvent, right, and it's defined here. So it can be it could be almost 100% of the CO2 contained in the with the solvent is approached equilibrium. That is no further split can happen. That's in that instance, right? So that's for that stage. So in that case, that's if we specify a equilibrium of 1. Or for CO2, it's typically from 0.2 to 2.4. Because then we are saying that 25% of CO2 in that stage is approached to equilibrium before going to the next stage. Okay, so 0.25 for CO2 approach to equilibrium. And for H2S, 1 is recommended for H2S. I mean, you see the guide. We have a guide here that actually helps to provide some of the theoretical underpinnings, okay, that guides specifications and the recommendations that are provided here. Okay, all right. So to specify that, what else do we need to specify? I think we are good. So let's run the simulation and see what we have. Okay, let's run the simulation and see what we have. Solving. Good. All right. Okay. So there's a warning here. Standard warning expected, telling us about the solution we have is 15 to 25% accurate. Okay, which is ideal for LensaSim. So just for you to know that is 15 to 20% accurate. Okay, so let's look at what we have, the solution. Right, let's look at the solution for G103 now. Now, of course, we're interested in seeing what has happened to CO2 and H2S. To CO2 and H2S. Remember. So now we compare to a G102. Right? G102 is the gas stream from which it's coming. It's the flare gas that is coming before turning to the sweet gas. So let's see what has happened to CO2. Okay, in mass flow, right? So G103 compared to G102. All right, mass flow rate now. Got CO2, right? From 548.6 kilogram, it is now 1.829. Essentially, almost all the carbon dioxide, over 99% of the carbon dioxide has been removed, right? And for H2S, everything has been removed. It's now 0, right? Okay, so what you could see that almost all the CO2, right, and the H2S and all of the H2S has been removed completely from that stream. Over 99% separation is fine, right? So essentially we've achieved the purpose. The main sweetening units has helped us to remove the very dangerous CO2 and H2S contained in that stream, because if you don't remove them, they're going to cause massive problem for the plant, leading to loss of $1 billion investment. So we don't want that to happen. So we've removed CO2 and H2S before we proceed with the processing. But of course, we still have water vapor. As you can see here, water vapor is still there. So we still have to do something about it, right? I told you it has the same sort of impact as CO2, right? So the sweet gas is still not dry, okay? Still has some condensed water entrained in the gas stream. So we have to remove that. Now, so the administrative unit is an absorption tower, like I told you. Okay, moves, and we have an absorbent in MDA that removes the CO2 and H2S as gases from that stream. We have what is known as a molecular sieve dehydration unit that is used for removing water vapor from a gas stream like this. So and why administration is an absorption tower? That is an absorption tower. For absorption, the H2S, the acid gases, are absorbed within the MDA, right? But for adsorption, the water in this case gets stuck on the surface of an adsorbent. Usually the zeolite is one of the adsorbents used for this kind of process. So the unit is known as a molecular sieve dehydration. Now, in LensaSim, we don't have a specialized unit called molecular sieve dehydration, all right? Okay, but this is where I'm going to tell you about what makes a process simulator. Now, a process simulator is an individual who understands the process, understands the details of the process, and can determine, given the tools he has, given the simulator he has, what kind of equipment or model available to him can best represent, okay, or model that equipment as it is in reality. Even though you don't have exact units in the model, in reality we can't even have all the exact units. Even even the three-phase separator, their main unit, they are not 100% to specification the way the equipment is designed in reality. Of course, so but the process simulation is suitable for material and energy balance. It gives you equipment energy and material energy balance analysis, right? So what a process simulator do is to find the closest model or closest equipment that can approximate the unit. In this case, a molecular sieve dehydration. What unit do we have here under separation that can do that job? And I'm going to go with the component separator, right? We have a number of separators units here. So we'll go with the component separator. Now, why a component separator? Remember, what we're trying to do is to essentially remove the water vapor, remove all of the water vapor. And the absence of a specialized unit to do that job, a component separator can help us to remove the water vapor. And we have a gas stream, a sweet gas stream that is free of water. All right, so I'm going to use component separator and then of course bring that stream, turn into the inlet for the separator, and specify new outlet streams. Okay. All right. So this, of course, would be, we call this now sweet dry gas, right? Sweet dry gas, because now we no longer have either acid gases or water vapor. After the step, we won't have them, right? In that gas chain. So sweet dry gas, and this would be the water, right? We'll just call it water. Okay. Oh, sorry, I was naming this. So this sweet dry gas, and we're gonna name this stream G104. Yeah, G104 and W102. I think we have W101 already. So yeah, W, right. So call it W102. So G104. Okay. So what we need to do now is to specify this separator. What to specify to the way it's working. LensaSim is we have you can specify it can be 2 products, right, or more. Right? But of course, all we need is 2 products. We just need the sweet diagram stream as well as the stream for the water, right? Okay, so 2 product stream. Now balance, then we have to specify balance products. Which product stream receives the remainder? Okay, so you have to specify which of these product stream. The first one, this sweet daggers, or the second one, water vapor. So essentially, what is saying that assuming we have to remove 70% of the water that is coming in, okay, from the sweet gas, as we want to remove 70%, then the remainder 30% will go into product 2. If we are saying this product 2, that will have receive the remainder. And product 2 corresponds to water, but that's not what we want to do. We want to actually remove all of the water, right? So, and we want the rest, the remaining. We want, let's say we leave, we are not able to remove 10%, then that 10% will go to the gas stream, right? So the remainder will go to the gas stream. Okay, so remove the water vapor. The water vapor, of course, has to be a split fraction to water. Okay, so but we are going to assume that we remove everything. Okay, so we can specify and just say 1, right? So it means all of the water vapor coming in, right? Coming in to the separator is completely removed, so that we have a gas stream that is free of water, and of course, essentially free of the acid gas. So just specify this, and I think we are good to go. Okay. Now, another thing I want to talk about is we have a note in LensaSim for, I mean, you can explain the basics so that when you come back later on to this to look at, to open your flow sheet and see what you've done, you can explain the rationale behind what you've done, right? So you can say, of course, this is supposed to be a molecular sieve, right? This is a molecular, like I said, a molecular sieve dehydration unit, right? So let's just, okay, let's talk like replacement, right? For replacement molecular sieve. So you can just make a note there so that either you or someone else that is looking at your flow sheet can see what has been done and can explain further the rationale for making that choice, right? So it helps in documentation. Okay, so we specify that and let's just run it and see what we have. Okay, good. So that's been solved. So let's see what G104 is contained now, right? What G104 is contained of. Okay, let's look at the water vapor, right? Of course, there shouldn't be any water. Yeah, right. So there's no longer water vapor contained in G102. Of course, no more hydrogen sulfide. We have some CO2. Of course, but hydrogen sulfide is gone. Water vapor is gone. Just some CO2 that is left. Okay. So essentially, we now have what is called a sweet dry gas that is ready. I'll say this. That is ready for the next step. That is now ready. We now have a sweet dry gas stream that is ready for the next step in the process of converting flare gas to olefins, right? So that's what we have now. Okay, And one other thing, let me show you one more thing before we conclude, right? So we can also, using the typical naming convention as well, we name all of these units. Okay. This is a mixer, call it mix 101, 100, mix 101. This is separate, right? All that we have done here is actually separations. So this is separation. Let's call it sep 101. Okay. This is also a separator. Okay. It's doing a separation work. So sep 102. Okay. This is also a separator. Sep 102. All right. So, okay. So with this, we've essentially come to the end of this simulation exercise. But of course, we don't want to lose, because this is just part one. In part two, we are now going to take the sweet jar gas, send it to a cryogenic separation unit. Okay, that is sub-zero temperature units, temperature below 150 degrees Celsius. Right. So that will be the next steps. Okay. So we don't want to lose this, what we've done. So we're going to save it. Let's call this flare gas. Name it flare gas to olefins. All right, flare gas to olefins, and then we have a save button here. So save. So and then that is save to locally and sync to the cloud. Okay. All right. And you can see it here. It's saved as flare gas. Okay. So with this, we've come to the end of this exercise, and I hope you've learned one or two things on how to at least get started with simulating a process like this, and perhaps you can also lay your hands on this, right? Use some of the data we've used in this exercise to using LensaSim, right, to try to do it yourself ahead of the next time we meet. Thank you very much. See you the next time for part two. So watch out for it. Watch out for part two. We're coming soon. Thank you.